Hello and welcome. My name is Markus Schnapping and I'm going to present joint work we did with Arno Fietzke from the company Itestra and Alex Pretschner. The paper has a title Defining a Software Maintainability Dataset. You might wonder, why is this actually complicated? Because in this context, we are not talking about crawling data from the internet, extracting information from documents or any other sources. We're talking about a dataset that is based on expert evaluations of software. So in the paper we describe how to collect, aggregate and analyze manual assessments of software maintainability. So what makes our research unique really are the experts. So who are the experts? In our study, 70 people participated. These are mostly developers working for one of the companies you can see on the slide, or who are not developers, but really software analysts. For example, Itestra is a company that offers quality-based reviews to their customers, and the people who do these really know what they're talking about when it comes to software maintainability. The largest group of participants are actually the employees of Itestra. In total, we collected almost 2,000 ratings of code. When I say code, I have to mention that this study is just based on Java code for several reasons. And the evaluated code was taken from 9 different projects. 4 of them are commercial systems and 5 are open source systems. The experts' time is actually our most valuable resource. So it is crucial to carefully select which code we present to the experts and have them analyze it. This selection approach is based on software metrics and clustering, and it is explained in detail in the paper. In this presentation, unfortunately, due to the time limit of the presentation, we cannot explain it here. But after selecting the code, we show it to the expert, and that happens on an online labeling platform that we created. So the experts can see the code. It is viewed in a text box like the one you can see here on the slide. They read the code and then they rate it according to several dimensions. For example, we ask them if they believe the code is easily readable and if they can easily understand the semantic meaning of the code. Their opinion is captured with a 4-fold Likert scale, as you can also see it on the right side of the slide. And every code snippet is evaluated by at least 3 experts. This is because we don't want to rely on the subjective opinion of just one single expert. So once we have several votes from the participants, we have to somehow aggregate the vote. For this, we do not use a plain average, but we use a weighted average, and we apply more weight to the votes of the most reliable experts. How to determine the most reliable expert is also one of the contributions of our paper and is also explained in sufficient detail in the paper, but it does not fit into the presentation time limit here. So based on the different reliabilities of the experts, the result of our aggregation is then presented in the form of a vector. That vector denotes the probability for each class on the Likert scale to be true. So the first cell of the vector denotes the probability of the first answer of the Likert scale to be true. For example, on the example on this slide, there is an 80% chance that the true label is the first option of the scale. This vector can be interpreted in several ways. For example, you just consider the class with the highest probability as the final label, or you compute something like a weighted average by multiplying each answer and its probability. Probably the most interesting question that we asked the experts was, overall, do you think this code is maintainable? And now I'm going to show you the results of this assessment. The pie chart visualizes that in 53% of the cases, the experts fully agreed, yes, this code is maintainable. In 25 of the evaluated code snippets, they slightly agree it is maintainable. In 14% they disagree, and in 7% they fully disagree that this code is maintainable. So these 7% are really, really bad code examples. What sticks out from this figure is the imbalanced distribution of the data. So the majority of the files is actually considered quite easily maintainable. And this imbalanced nature is not ideal. For example, if you want to train machine learning models on the dataset. But still, we believe the data to reflect the real world. And this imbalanced distribution is also aligned with what related work reports and is also aligned with our own experiences from several quality reviews. In total, we managed to label 519 Java classes. This is not a very large number, but please also keep in mind that every class was evaluated by 3 or 4 experts, and that if you compare this number with existing data sets, actually 519 is not too bad. So this is one of the results of our study, and the other contributions are the following. Like I already explained, we came up with a sampling and prioritization methodology how to select the code that we're going to present. Then one insight is that experts indeed disagree, and they disagree frequently and significantly. So to overcome this dissent, we apply a mechanism that determines the most reliable experts and provides them with more weight. We also analyze the rating of the experts and report what they took into account during their assessment. Finally, the dataset, that means the code plus the manual label, are made available to all of you on figshare.com, and you can access it using the QR code on this slide or the tiny URL that you can find at the bottom of the slide. It is also referenced in the paper, and I hope that it is useful for some of you, or maybe all of you. And I'm looking forward to the Q&A session, and thank you very much for your attention.